Welcome to the EPG Padashala, the lecture series in computer science for the PG program, and this is the 14th module of the subject compiler design, and this module discusses about the SLR of 1 parsers and in particular construction of the LR of 0 items, which is a prerequisite for SLR of 1 parsers. The construction, the development team. The objectives of this particular module are to learn the steps involved in an SLR parser to start with, and then learn to construct the LR of 0 items. The keywords will be SLR parsers and LR of 0 items. Bottom up parsers. A simple shift reduce parser has lot of shift reduce conflicts, which we have already discussed. So, where the concepts will be just a shift and a reduce. So, if you could shift, else try to reduce. So, at one particular point, whether to shift or to reduce will be an issue, that is called as a shift reduce conflict. So, that is a major drawback of a simple shift reduce parser, and if the grammar is ambiguous, the problem multifolds, the sense that there will be so many shift reduce and a reduce conflict. And the next bottom up parser, which is an operator precedence parser, is for a small class of grammar. Okay, it cannot parse any grammar. So, therefore, this is a drawback of the operator precedence parser. So, therefore, we normally go for LR parsers. LR parsers in the sense that it is left to right scan. The first L stands for the input is scanned from left to right, and the R stands for rightmost derivation. Now, here it also says reverse rightmost derivation, in the sense that when I look at rightmost derivation, I will start from the symbol and then start constructing the LHS for production, start replacing the RHS with the LHS, but it is also a reverse rightmost derivation, in the sense that you look for a handle. Okay, the handle will be looked upon from right to left. So, that is a reverse situation, and in which one symbol of look ahead is sufficient to decide whether to shift or reduce. This one here indicates you are looking for one symbol at a particular point of time. So, here LR parsers, what does it do? It read an input one token at a time. It uses a stack to keep track of current state. The state at the top of the stack summarizes the information below. The stack contains information about what has been parsed so far. Okay. So, it keeps a track of a stack and the stack state at the top of the stack. So, that stack will basically have a state and input combination. It can have state number, it can also have terminals, it can also have non-terminals. So, all these things will be in the stack. So, depending upon what state the top of the stack reads, you will be in a position to understand what string has been parsed so far. Okay. Now, it also uses a parsing table to determine action based on the current state and look ahead symbol, whether to push, whether to pop, or everything is done with reference to a parsing table which is being constructed. So, as in the other cases, the parsing table construction is going to be the primary job. Now, the parsing table will have actions like shift, reduce, accept or error. So, whether to shift at a particular combination, whether to reduce at a particular combination, or should I accept and stop parsing, or is it going to be an error routine call that is indicated in your parsing table. Okay. So, that is the primary objective of the LR parser. So, you have the parsing table, you have the input, you have a stack. So, using these three you will end up in parsing a particular string. So, LR parsers can basically be classified into three categories: simple LR, canonical LR and look ahead LR. Okay. So, simple LR, it is as the name itself suggests, it is going to be simple LR parsing. It is easy to implement, but it is not powerful, and it uses what is called as LR of 0 items, okay, for construction. The parser is a SLR of 1 parser. It has one look ahead symbol, but the items which is constructed, this item set is the basis for constructing the parsing table. That item set construction is basically what is called as an LR of 0 items. And then you have one more thing called as canonical LR parser. It is a larger parser, but it is powerful. Okay, it is the construction is going to be difficult, but it is going to be a powerful parser, and it uses LR of 1 items for the table construction. Okay. as against LR of 0 items here. This is also canonical LR of 1, that is you are using only one symbol look ahead here also, but it uses LR of 1 items for its constructing the parsing table. Okay. The next class is called as look ahead LR, which is a condensed version of canonical LR. It may introduce conflicts, and this also uses LR of 1 items for its construction. So, this also uses LR of 1 items, but it is going to be a condensed version of canonical LR. So, this is also basically preferred. Now, SLR parsers is what we are going to start this module with, and we have already seen what is a handle. A handle is a substring of a string that matches the RHS of a given production at a particular point of time. As a SLR parser processes the input, it must identify all possible handles. So, for example, consider the usual expression grammar and the input string A plus B. Now, if the parser has processed A and reduced it to E, then the current state can be represented by typically here E dot plus E. So, this is how you represent a particular state. So, you are looking at the same expression grammar and your string is now A plus B. Now, how the SLR parser work is what we have shown here, E dot plus E, where the dot means E has already been parsed, this E, okay, the first E has already been parsed, and plus E is a potential suffix which is, if it is found out, it will yield to a successful parse tree. So, that is what we are talking about as SLR parser. So, the primary behind this handle here is by means of looking at what this dot basically tells you. Now, you are going to use a dot to indicate how much you have parsed and how much more is left for parsing. Okay. So, this how much has been parsed, okay, indicates it has been successfully parsed, and what is left to be parsed, okay, it is a probability that this is possibly a definite suffix, okay, and that can be considered as a handle. That is what we are talking about here. So, this dot is important. Now, how do I place this dot and what the dot actually indicates? Okay. Can the dot be in any position? All these things have to be understood. Now, our ultimate aim is to finally reach a situation where you will have a dot at the end which corresponds to an actual handle yielding to the reduction E produces E plus E. So, if you have the dot at the last position, that is after the E, after the last symbol, if you have a dot, that indicates that you have successfully parsed and E plus E is going to be a handle. Okay, that is your understanding here. Okay. Now, LR parsing works by building an automata where each state represents what has been parsed so far and what we intend to parse after looking at the current input symbol. This is typically indicated by the productions having a dot. Okay, these productions are referred to as items. So, we said LR of 0 items is what is to be constructed by the SLR parsers. Now, how do I construct these items? To construct these items, I need to position a dot. So, in the grammar, if the RHS has a dot, that is looked upon as an item. Now, how do I construct this item? And for the SLR parser, it requires what is called as an LR of 0 items. Okay. Now, this item that has the dot at the end leads to the reduction by that particular production. Okay, we will see this concept with the example. Items which has got a dot at the end for any given production means that I could reduce at this particular state with this particular production. That is the understanding. So, this is a typical situation of your LR parsing program. You have a stack, okay. The stack has got symbols and states. The input has got symbols, terminals A1 to AN, again terminated by a dollar. There is a parsing table here which has got two sections, action and Goto, okay, and this is typically what we call as a DFA, okay, what we represent as a DFA, but you can also represent it as a table and show that it is okay. So, the program looks at the input, uses the stack and the parsing table and checks whether it is successful parsing or not successful parsing. That is your output. So, output will be a successful parsing and you will have a parse tree if it is successful. If it is going to be unsuccessful parsing, you will not have a parse tree here, you will say an error situation. So, from you have to basically the steps are form the augmented grammar. Okay. Now, what is the augmented grammar? Adding one production, okay, as the beginning production and changing the start symbol is what is called as forming the augmented grammar. And then construct the LR of 0 items, and then construct the follow for all the non-terminals, again which requires construction of first for all the terminals and non-terminals. So, find the construct LR of 0 items and then construct follow and first for all the terminals and non-terminals. And then using this item set and the follow of the grammar, construct the parsing table. Okay? And using the parsing table, use a stack and a given input can basically be parsed. So, an LR of 0 item of a grammar G is a production of G with a dot at some position of the right hand side. This is looked upon as a LR of 0 item. For example, you have a production. This example is from the Ahoseti-Ullman textbook. So, A produces XYZ is a production. It has got 4 items. The dot can be in the beginning or after the first character or after the second character or after the third character. So, these are 4 possible items. And supposing if I have a production A produces epsilon, then A produces dot is going to be the only one item. This parser does not require the grammar to be pre-processed, or there is no prerequisite here. Any grammar can be parsed, only thing is you have to convert this grammar to an augmented grammar. Augmented grammar means you have to add one new production, okay, and that production will be a unit production. Unit production is LHS is a single non-terminal, RHS will also be a single non-terminal. So, A produces A dash or A dash produces A, that is a production. This A is going to be the existing grammar's start symbol. Okay. So, that is what we are going to have here. The grammar is augmented with the production, S dash produces S, new start symbol is S, S dash, existing start symbol is S. So, this is the augmented grammar. Now, this calls for 2 possibilities, 2 steps in constructing the LR of 0 items. First one is called as closure. Okay. So, let us say C is equal to closure of S dash produces dot S. So, I have to call the function closure with this as the item to start with. Okay. This is an item because we just now said if there is a dot at any position, that is called as an item. So, I am going to call the function closure with the dot at the first position of the new production of the augmented grammar. And then for each set of items I belonging to C, C is your closure, and for each grammar symbol X belonging to non-terminal union terminal such that Goto of I comma X does not belong to C and Goto of I comma X is not equal to null, add the set of items Goto of I comma X to C. Okay. For each of the non-terminals, okay, and the terminal, you have to find Goto of I comma X. If it is not belonging to C, that is if it is not already available in C, you find that, and it should not be empty also. Okay. You find that and you add the set of items Goto of I comma X to C. Now, what is this Goto computation? What is the closure computation? That is what we have basically C. Repeat until no more sets can be added to C. So, C is going to be this set of items which you are going to compute. To start with, we will compute with closure. Now, what is closure of a item I? So, item is given here. Item means what? The production with a dot at any particular position. So, start with closure of I is equal to I. So, whatever is given, that is your first point, starting point. Now, here if A produces alpha dot B beta belongs to closure of I. Now, what am I looking at here? There is a non-terminal here. Before the non-terminal, there is a dot. Okay, before the non-terminal, there is a dot. Then, for each production, B produces gamma in the grammar, and the item B produces dot gamma to I if it is not already in I. Meaning that you look for every item. You start with the initial item I. A produces alpha dot B beta. If there is a dot before a non-terminal, for you add the items of that non-terminal. Item means what? You have to add the production with a dot in the beginning. So, that's what it says. B produces dot gamma is added to the item I if it is not already present. Repeat this step until no new items can be added. So, this is closure of I. Okay. So, for every item I, this has to be done. Now, how do I choose the item which one to start with? I already know I have to start with the new production, which is the augmented grammar's production. And how does Goto gets computed? Goto of I comma X, that is if there is a dot before any symbol, this x can be a terminal or non-terminal, I have to do that. I have to compute Goto of I comma x. So, for each item alpha dot x beta belonging to I, add set of items closure of A produces alpha x dot beta to the Goto of I comma x if it is not already. That is, Goto of I comma x is computed by shifting the dot by one position to the right. That is, what is this? Okay, Goto of I comma x means shift the dot by one position to the right, okay, and that will be Goto of I comma x. Again, I have to carry out repeatedly in the sense that again if beta, this beta is going to be a non-terminal, you have to keep adding the items closure of I in the set. If you remember the previous slide, again it falls under this particular category. So, I have to keep on iterating Goto and closure. Okay. So, repeat until no more items can be added to Goto of I comma x. So, you shift the dot by one position, that is the first element, and then you have to consider, if you remember that this is add the set of items closure of this, the sense that first you add this item, you shift the dot by one position, and for this as an argument you call closure, okay. That is Goto of I comma x. So, you have to find closure of I and Goto of I. If you remember LR of 0 items, it starts with closure of this, okay, and then you have to consider Goto also. So, what do we say? Closure will be just looking at that particular production, adding that, and if there is a dot before a non-terminal, you add the productions of the non-terminal with a dot in the beginning. This is closure. I am constructing one item here, one item set here, okay. Now, Goto will be done for all I comma x, where x can be a terminal or a non-terminal, where this x is appearing after the dot. Now, to start with, in Goto of I comma x, I have to check this Goto of I comma x will be some I1 or I2, whatever it is. I have to shift the dot by one position, and with this as an argument, I have to call closure. When I say I am going to call closure, if beta begins with a terminal, I stop there. If beta begins with a non-terminal, then I have to call closure, which is nothing but adding the productions of beta with a dot in the beginning, and I have to keep on iterating until no more new items can be added. So, repeat until no more items can be added to Goto of I comma x. So, that is your situation. Intuitively, Goto of I comma x set of items that are valid for the viable prefix gamma x when I is the set of items that are valid for gamma. So, this is the interpretation. We will come back to this in the example. Okay, consider the expression grammar, which is going to be your unambiguous expression grammar. So, this is the grammar, and so I am introducing a augmented production here. So, I have to now first call closure of E dash comma dot E dash produces dot E, okay. That is your first set, that is my I naught. So, I am going to call this as closure of E dash produces dot E. But what is this condition? E is a non-terminal appearing after a dot, therefore, I have to add the productions of E with a dot at the beginning. So, E produces dot E plus T and E produces dot T. Again, look at these two productions. This has a E after a dot, so no problem, we have already added the productions of E. This has a T after a dot, so I have to add the productions of T again. So, which is nothing but T produces dot T star F and T produces dot F. Okay. Now, this there is no problem, I have to add the productions of F now. Okay. F produces dot open parenthesis E close parenthesis and F produces dot ID. Okay, it is not like I completely copy paste the grammar and then put a dot in the beginning. That is not the situation. The situation here is I have to start with the first production, that is the augmented grammar's first production with a dot in the beginning. I have a non-terminal here appearing after the dot, I have to add its productions, which I have done here. Then this is again a non-terminal appearing after a dot, add the productions of T, add the productions of F, that is what I have done. This is I naught. Now, I have to compute Goto of I naught comma E, I naught comma T, I naught comma F, I naught comma open parenthesis and I naught comma ID. So, I naught comma E. So, how do I do that? I have to shift the dot by one position, okay. In these two productions will now qualify for I naught comma E, because these two productions have got a E after the dot, okay. So, that will be Goto of I naught comma E which is E dash produces E dot and E dash produces E dot plus T. Then I2 will be Goto of I naught comma T, I will come back to this later, Goto of I naught comma T, that is looking at the RHS, wherever there is a T appearing after the dot, I have to take that and shift the dot by one position to the right. So, E produces T dot, T produces T dot star F. Now, here there is a star appearing after the dot, so no problem. Here also there is a star plus appearing after the dot, there is no problem. Had this been a non-terminal, I have to repeat the process. Okay. So, next one is I3, which is Goto of I comma open parenthesis. So, open parenthesis, I shift the dot by one position, I ended up E. E is a non-terminal. So, add the productions of E with a dot in the beginning. Again I have a T. Add the productions of T with a dot in the beginning. Again I have F here. Add the productions of F with the dot in the beginning. Okay. That is going to be my I3. Okay. Now, I4 will be Goto of I naught comma F, which is T produces F dot, shifting it by one position, and I5 will be Goto of I naught comma ID, which is equal to F produces ID dot. Now, I am done with I naught, but I have to yet still process I1, I2, I3 and so on, I4 and I5 if there is a dot appearing, okay, dot appearing before a terminal or a non-terminal. So, I6 will be Goto of I1 comma plus. Now, if you remember I1, it had E dash produces E dot and it has E produces E dot plus T. Now, I have shifted this dot by one position to the right and now I have a T. So, I have to add the productions of T. I have now a F, add the productions of F now. Okay, that is going to be your I6. Now, I7 will be Goto of I3 comma E. Okay, I have left I2, actually I will come back to that. I3 comma E, which is nothing but shifting one position to the one position after the E. So, this is over. Okay, I have a close parenthesis here, so it is over. And I have two productions in I3. Okay, I3 is a big set, remember. So, F produces open parenthesis dot E close parenthesis, I have a big set. So, these two will qualify for I3 comma E. So, I have shifted the dot by one position. This is a terminal, this is a terminal, so there is no problem. I8 will be Goto of I6 comma T, which is E produces E plus T dot. So, no more to process, and T produces T dot star F. These two productions will qualify. I have shifted that by one position. Now, I9 will be Goto of I7 comma close parenthesis. So, this is the only thing, I am done. I10 will be Goto of I2 comma star as well as I8 comma star. Okay. So, I2 comma star is also done, which is T produces T star dot F. I have to add the productions of F. Okay. And I11 will be Goto of I10 comma F, which is this. Now, all the other things would be repetitions. Okay. If you consider, for example, I am done with I3, okay, nothing to consider in I4, I5 also there is nothing to consider, I3 there is so much, okay. I3 comma E is there, I3 comma T is there, I3 comma F, I3 comma open parenthesis here. I3 comma open parenthesis will be the same set, okay. And similarly, I4 will be I0 comma F as well as I3 comma F, both will result in the same set. Now, I will call two sets as exactly identical if both of them have the same set of productions with the dot at the exact positions. So, I cannot call T produces dot F and T produces F dot as same. T produces F dot and T produces one more F dot will basically be same. So, this I4 will correspond to I0 comma F as well as I3 comma F as well as I6 comma F. I0 comma ID, I5 corresponds to I0 comma ID as well as I3 comma ID as well as I6 comma ID and I10 comma ID. Now, all these four Gotos will result in F produces ID dot only. Okay. Now, if you consider again here, I6 will be I1 comma plus as well as I7 comma plus. Okay. I1 comma plus is what? Just shifting it by one position. E produces E plus dot T, and then I have to add the productions of T and then the productions of F, etc. And this will be the same set if you get I7 comma plus also. That is, Goto of I7 comma plus will also result in the same set. So you have to keep on repeating until no more new productions can be added to the item set. So I6 is now this set. Now you look at I7 is actually Goto of I3 comma E. So I3 comma E means I had two productions, one is open parenthesis dot E close parenthesis, other one is dot E plus T. So two have to be considered, okay. I shift the dot by one position and that is what resultant of I7. Now I7 comma close parenthesis has to be done, that is what we have done in the later section. I7 comma plus, how will that look like? That will be again similar to the previous one, which is I6. So I7 comma plus and I1 comma plus will be exactly same set. So for moving the dots and for looking at the Goto, I should look at the RHS of the production and check whether the dot has basically matched, where which position the dot has basically appearing. So I have to now find out I6 comma T, I6 comma I6 comma T, these two will qualify. So T has a here, T is here with the dot in the beginning, T is here with the dot in the beginning. So these two will qualify for Goto of I6 comma T. Goto of I6 comma F, this will alone qualify. Okay, if you look at Goto of I6 comma T, I can take that as a final example. And so Goto of I6 comma T, two productions has to be considered as set, which is E produces E plus T dot and T produces T dot star F. Okay. So I9 will be I7 comma close parenthesis, only one situation. As you could see, some items have a dot at the end. That means that this will be a possible handle for reduction. Okay. And I10 is nothing but I2 comma star and I8 comma star, which is T produces T star dot F at the productions of F. Okay. And similarly, so what happens here, I10 comma open parenthesis will be again the same set I3. I10 comma ID will be the same set, which is nothing but I5. Okay. So if you keep on repeating, this is going to be your situation. So the ultimate aim is you have to keep on iterating until no more new items can be added. Finally, T produces T star F dot. So this is one more handle, because you look at it, there is a dot at the end. So this is how you construct the items for the SLR of one parser, which is called as the LR of 0 items. So this module we discussed about the steps involved in SLR parser, which is constructing the LR of 0 items on an augmented grammar, and then constructing the follow, and then constructing the parsing table, and then using the parsing table which is constructed. This calls for constructing of the LR of 0 items, which is what has been discussed in this particular module. Thank you.